Hey guys, welcome back. I hope you guys are all doing well. Today I just want to go over like two really quick kind of specific types of sequences that are important. You'll see them come up again when we start talking about series. Um, First one is a geometric sequence. Now you may remember this from geometry or someplace else, one of your other classes. But a geometric sequence would be like the following, right? It would be like 2, 6, 18, 54, 162, and so on, right? This here is a perfect example of a geometric sequence, okay? Why is this geometric sequence? Well, you may notice that going from one term to the next term, it just looks like we are doing what? Well, it looks like we're timesing by 3. That every time you go from one term to the next, it's just a product of 3. You take your previous term, multiply by 3, you get your next term, right? So I could write this as 2, 2 times 3, 2 times 3 squared, 2 times 3 cubed, 2 times 3 to the 4th, and so on, right? We can see that each term is just an extra multiplication of 3, of this common factor, this common, we call it a common ratio, all right? 3 is, all right? And so we might actually denote this series as a sub n is equal to your first term 2 times 3. But notice you don't have 3 to the first here. This would be 3 to the 0. This second term is 3 to the first. The third term is 3 to the second. The fourth term is 3 to the third. So we could write down here n minus 1. So your nth term is not going to be 3 to the n. It's going to be 3 to the n minus 1. And that is your general term for this particular geometric sequence. All right? And in general geometric sequence would be like a sub 1, a sub 1 times r. Your common ratio would be r. A sub 2 times r squared. I'm sorry, that's still supposed to be a sub 1, not a sub 2. Excuse me. And this will be a sub 1 times r cubed. A sub 1 times r to the 4th, and so on. We could say a sub n is equal to a sub 1, sometimes they'll call that a sub 0, times r to the n minus 1. Tends to be our typical geometric sequence. Okay? Now, just like we started doing with our other sequences, we can talk about the limit of a geometric sequence. And the limit is really going to depend upon what here? It's going to depend upon r. What is that common ratio? All right? Multiplying by that a sub 1 at the beginning isn't really going to matter so much. It's more what is happening to that r to the n minus 1. Well, we're going to really have 3 cases for what can happen to this limit of a geometric sequence, which is based upon that common ratio there. And basically, if your common ratio is greater than 1, we know that this is going to be shooting out to infinity, or we could say it's going to diverge, right? Of course, if r equals 1, well, then your sequence really isn't very interesting. It's just going to be whatever that first term is, right? Because all of those a sub 1, this is still going to be a sub 1 and a sub 1 and a sub 1 and a sub 1 and so on. Now, if your common ratio is less than 1 but greater than 0, then you're going to have a fraction. So, for example, your common ratio might be able to take half of a sub 1 every single time, half of the previous one. So, whatever a sub 1, this will be half, and this is 1/4 and 1/16 and or 1/8 and 1/16 and so on. This is where we have a nice convergence to 0. Our terms are going to end up decreasing and getting closer and closer and closer and closer and closer to 0. Of course, if your r is negative, all that means is our sequence is going to be alternating. So I could say if r is less than -1, this here is just going to diverge. And it's not going to diverge to positive infinity or negative infinity. In fact, it's going to get infinitely big and infinitely negatively big as well, right? I mean infinitely small. So, every even exponent, or every even term, or actually it'll be odd terms, will end up being positive. Even terms will end up being negative, because it's n minus 1. So, it's going to be both your odd terms shooting out to positive infinity and your even terms shooting out to negative infinity, in which case they both don't just go to one place or another, okay? So be careful of that negative common ratio between terms, right? Now, if you're from 0 to -1, let me write that this way, -1 less than r less than 0, this will converge to 0, which will be nice. And if your r is just equal to -1, this is going to diverge and go nowhere. It's not going to go to a sub 1 because, your odd terms will be positive a sub 1 and your even terms will be negative a sub 1. So it just doesn't really effectively go anywhere. So this is our geometric sequence. All right, you will experience more of this, especially when we move on to series and we talk about geometric series. Okay. Now the last special sequence is going to be very kind of obvious to you. At least I hope it is, and that is that special sequence a sub n is equal to 1 plus k over n to the nth power. Hopefully you're like, oh yeah, I know that. That's kind of obvious, right? I mean, we did this as functions, and of course, the reason why this is an important sequence, or something that we recognize already, is that the limit as n goes to infinity of 1 plus k over n to the nth power. Of course, this is where k is a constant. We know that this limit is just going to be e to the k. All right. So those are the two sequences I wanted to go over today that are special. Please keep your eye out for geometric and pay attention to that common ratio, right? What does it take to multiply going from one term to the next term? That common ratio is important, and it's important for being able to find the limit of a sequence. So we'll be doing some more with that later, all right? Thanks, guys. Have a good day.